back to our last problem on our practice exam 3, our practice final exam. So let's look at our RV below, which represents a cube of aluminum. So once I hear aluminum, what do I know? I know that this is going to be this modulus of 69 times 10 to the 9 Pascal. My nu is going to be equal to 0.3. So let's go ahead and let's write those to our fresh and clean Mathematica notebook. So y is equal to 69 times 10 to the 9. Let me get that capital Y. And let me clear all quit my notebook. So we got that value here. My nu is equal to 0.3. And let's get going here. Excellent. So let's look at the RVE below. And actually, let's go ahead and let's write out our stress tensor. So I know that here we're going to have a sig 3,3, and that's going to be red. My green is going to be my sig 2,2. There is no sig. Oh, excuse me. Not there, Professor Steimel. My sig 2,2 is going to be right here. So I've got a sig 3,3 that's compressive, negative. I've got a sig 2,2. I don't have a sig 1,1, so I'm just going to kind of draw this as black 0. And then what's going on this blue? So what's the normal to this face? That's the 2. What's the direction? So that's sigma 2,3. So sigma 2,3, sigma 2,3, and everything else is 0. And then the other question we have to ask is, will that rotation give us a clockwise or counterclockwise rotation? So I'm rotating around this way, so that's a counterclockwise, so that'll be positive. So let's go ahead and define those values. So my sig 1,1 is equal to 0. My sig 2,2 is equal to 17 megapascals. Whoops, not word. Don't need word. So sig 2,2 is equal to 17 times 10 to the 6. My sig 3,3 is equal to minus 55 times 10 to the 6. And let's keep going here. And I pretty much think that's about it. So let's go ahead and let's look at our strain tensors. So what strain components exist? I don't have a stress in the 1,1, but I do have a stress in the 2,2. So I'm going to have strain in 1,1, strain in 2,2, strain in 3,3. And I'm also going to have no strain here, but I will have a strain 2,3, strain 2,3, 0. So let's go ahead and write out these tensors quantitatively. So I'm going to go ahead and do this. Let's go ahead and let's take a peek at some of these problems. So let's do that E11 is equal to 1 divided by y times sig 11 minus nu times sig 22 plus sig 33. Again, these are just kind of calculations at this point. And that kind of makes sense because, again, as we're compressing it more than we're extending it, so that kind of hopefully makes sense. So it's positive. Sig 22, sig 11. And I can do the same thing. Again, very similar. Again, I'm pulling in that direction. But my 3,3, I bet you this is going to be a negative. Actually, it better be a negative. So let's go to 3,3 minus nu times sig 11. Oh, and then we also have that makes sense. Sig 2,3 is equal to 78 times 10 to the 6. And I know that my E23 is equal to 1 divided by y times 1 plus nu times sig 2,3. There you go. Shear stress, shear strains, everything. My tensor notation. That's it. Draw the Mohr circle. What is the rotation to get to principal stress? What about maximum shear? Well, we know that, for example, look at this. My 1,2 plane. So for 1,2, my stress tensor looks like this. My sigma 2,2 is 17. These are all megapascals. We are in the principal stress state to maximum shear. That's 45. What about 1,3? So this guy, this guy, this guy, and this guy. So for 1,3, very similar, except this is going to be, I think, negative 55. So negative 55 here, here. Again, in the principal, 45 here. What about this one here? This is where we get a little bit nasty. So again, we've done this previously, so I'm going to go ahead and do my shortcut. And actually, I need to pull in. That's why it's always handy to have an old notebook ready to go. I need my rotation matrix. Got to figure this out. So pull this in, pull it into my notebook. Any of this is T. There we go. So now in this system, I've got, so my stress OG is going to be equal to sig 22, sig 33, and then sig 23. Let's take a peek at that. Excellent. So now we just have to kind of figure out, okay, we need to figure out when are we in our principal stress state. So I'm going to go ahead and take solve for when T dot stress OG, the third component, when does this equal 0 in terms of theta? Theta here. So let's look at this numerically, and I could again pull out the smallest value. So right here. So I need to go 32 degrees again if I were to kind of draw this out. So let's go ahead and let's draw it out. So if I'm looking at my 2-3, I'm looking at my stress state. I've got actually, let me draw it a little bit different. So let me draw it like this. So I've got minus 55. I've got what else do I've got here? Got my 2-2, which is 17, and then I've got basically 78, 78. So I've got points here, 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 here. So I draw my circle. If I'm looking like this, I figured out that 2 theta. So the theta to go from here to here is going to be that 32. So the theta to get to principal is just going to be 45 minus this. Oops. Like we've done previously in class. That's it. All right. So we've identified three principal stress values. Again, so we can do that. Eigenvalues of my full stress is going to be this. So my stress is going to be, there's 0 here, 0. I'm trying to do this by memory. 0, and then it's going to be 0. My sig 22 is 17 megapascal. 17 times 10 to the 6. 78 times 10 to the 6, and then 0, 78 times 10 to the 6, and then minus 55, right? Yep, 55 times 10 to the 6. Those values. Let's look at stress in matrix form, just to confirm. Yeah, that looks pretty much on the money. Eigenvalues of stress. Let's look at those numerically. There we go. That's our principal stress values. And let's see. We have one more little question. Here we go. A little bit into conceptual things. Okay, so I identified the 3 steps. I'm interested in processing my material to increase the yield strength. One suggested that I place RB in an oven at high temperatures for long times. Another wants to cold roll the material. Yet another wants to add some solute material in hopes of precipitating on a second rank, which process will lead to the largest increase in yield stress. So, cold rolling, we know that our yield stress, our change in yield stress, scales as dislocation densities to 1/2. Our dislocation densities can vary from 10 to the 7th to values of 10 to the 14. So that's going to be our biggest push. Annealing will increase our grain size. So if we anneal and our grain size will increase, and we know change in yield stress is proportional to GG to the -1. And it will also, if we anneal, our grain size increases and our dislocation density decreases. So that will be the worst. And the secondary phase particles, that's where we get our kind of, again, cutting or bowing. So we cut here, we bow at larger particle distances, and there we go. So those are the different strengthening mechanisms. And then this is just a fun extra credit question. It won't be asked, unfortunately, this time. Where can you find a cow with no legs? Right where you left it. Thanks and congratulations, and that's the end of Engineering 45. So I look forward to seeing you in a future class. Thanks, and good luck on the exam.